Hello everyone, and welcome to the ALTA conference. I hope you've had a good week. My name's Peter Talbot, and I'm a professor at QUT and a program manager at the Future Battery Industry CRC. And today I'd like to talk to you about establishing a battery industry supply chain in Australia. This is particularly of interest considering the degree to which we mine battery materials. So if we look, just one second, if we look at the minerals that we would use in a battery, Australia's rich in battery mineral resources. It currently produces around 9 of the 10 elements that are needed in a lithium-ion battery in terms of anodes and cathodes. It also has considerable reserves of graphite, the remaining elements. So if we just look at those minerals, we've got lithium, cobalt, manganese, iron, nickel, phosphate, aluminium, graphite, copper, and titanium. And Australia is leading the world in the mining of these resources. So what I'd like to do is look at how we go downstream in terms of the value chain in producing these materials. So let's look at the opportunity first. So the battery market around the world is growing at a massive rate. The global lithium battery market, just for automotive vehicles, for EVs, is something around, it's going to reach around $95 billion by 2030, and it's growing at an annualized rate of around 14%. So this is a huge opportunity for minerals processing in Australia. If we take an example of one of the minerals in this value chain, say lithium, and we look through across where we've been in this process and where we're heading, if we go back to 2017, Australia produced around $1.13 billion from the mining and processing of lithium in Australia. So from mine concentrates, we had a significant input. But if we look across the value chain through refining, precursor and electrochemical production, battery cell production, and battery pack assembly, we didn't participate in what was a $156 billion industry. Our projections to 2025 show that while we will produce significantly more lithium from our mine concentrate, and we will start in refining processes, at this stage, we still only produce around $10 billion from something that is forecast to be about a $1.7 trillion industry, which is only around 0.5% of the value chain will be realized here in Australia. So this again is if we can participate through the process value chain and establish it here in Australia, there's an enormous opportunity for this industry. I take another example, graphite material. It's a principal material in the anode. And if we look at the moment in natural graphite, it sells for something like $500 a ton as a refractory. But if we process it downstream for a battery grade material and take it through processes such as spheronizing and purifying, coating that material, and then comparing it to what's being produced in synthetic materials, we have an enormous value add. Battery materials improve in performance, and particularly graphite, if we add nanosilicon. And that gives us around $20,000 a ton in value compared to $500 a ton for natural graphite. So we're looking at ways of actually developing these downstream processes in Australia, teaming up and collaborating with industry and research to be internationally competitive in these materials. First question, I guess, is what's inside a lithium battery? So let's just go back and have a look at the sort of way that these batteries are constructed. Typically, there's a cathode, an anode, and a separator material. So the cathode are typically a lithium transition metal oxide coated onto an aluminium substrate, electron collector. The anode is a graphite-based material. Again, it's coated onto a copper electrode, and it's got a separator membrane between the two. But the materials are typically powders. So the value add material here that we're talking about is powdered materials, powdered cathode materials and graphites, which we convert into inks and coat onto our batteries. I guess it's worth looking at just how these materials work. So a cathode stores the lithium and releases those ions during charging and discharging. The anode stores the lithium and releases the ions when the battery is discharging, and the materials are separated by a polypropylene membrane, and the ions are transported in a liquid or a gel that acts as a transport for the lithium ions. This is the electrolyte. Okay, so let's just look at what the different stages of establishing this value battery chain look like. So from our minerals extraction, we have a processing stage. Those materials, as I've just indicated, are turned into powders and coated onto electrodes. The electrodes are put together into cells in different formats, such as cylindrical, which you're probably familiar with, but also pouch cells like you would find in a computer or a phone, prismatic cells. These are then combined together into modules, and they're put together in packs. And then we see them go into applications, and an example would be integrated into a vehicle, into an EV. And of course, the final stage of a battery's life is hopefully a second life and through recycling. So as I've pointed out, there are a number of stages in the value battery chain, which we're trying to support and develop here in Australia. One way that we're going about this is through the Future Battery Industry CRC. The CRC is supporting projects which will help the development of the supply chain. So if we look here in terms of what that supply chain and support network might look like, we have extraction of materials, which we're doing, as I've indicated, very well in Australia. We've begun processing and refining of downstream battery chemicals. But the gap at the moment in our development is in the actual production of the cathode materials, the electrolytes, and the anodes. And then in order to produce cells, test them for performance, validate the materials, we need to have a system where we can do electrochemical testing and fabrication of cells here in Australia. And of course, in order for them to move into applications, we need to be able to test these as battery packs and modules. So the CRC is supporting this range of projects in particular to fill the gap and support industry in the development of this supply chain. An example in cathode manufacture is that the CRC has commissioned a state-of-the-art technical report for the assessment and process of cathode materials. So this report has confirmed the technical and commercial feasibility of forming and starting pilot scale testing here in WA. We look at the different minerals that are being produced, and we find that there are already groups that are advanced in producing some of these raw materials, particularly materials like cobalt, nickel, manganese, and lithium. So if we go back and we decide on which materials would we choose for production of a cathode material, we look at this spectrum of properties and the issues that we need to address to choose that material. So for example, specific energy, specific power, safety, performance, the cycle life of the battery, and its cost. There are a number of materials that we would use here. For example, and would be lithium iron phosphate is one of the compositions that we might look at. And you can see from this graphic how it fits in terms of these interaction of these different properties: high specific power and safety. It's slightly down on specific energy and performance. If we look instead at lithium manganese oxide, another potential material, you can see that how it compares to the previous sample. And again, with lithium cobalt oxide, this material's got very high specific energy, but its safety and specific power are quite low. A material that's used particularly in terms of vehicle manufacture for EVs is an NCA, which is nickel, cobalt, aluminum material. But the material which is coming to the fore with the greatest use in lithium ion batteries and applications is a material called NCM. So it's a lithium, nickel, manganese, cobalt oxide. So this is our material of choice for our cathode pilot plant. And if we look at what sort of precursors we need to develop, they're typically, in this case, sulfate precursors. So cobalt sulfate, nickel, manganese, and the lithium is in the form of a hydroxide. The purities that we need for these materials are around 99.98%. So cobalt, for example, Around 57% of cobalt used in batteries, and its form is 37% as sulfate. Australia is the second largest producer of this material. Nickel is the primary precursor in NCM, and it's increasing significantly in its introduction into the nickel-rich cathode compositions. Manganese is particularly is not produced in Australia in great amounts, and over 87% is produced by Chinese suppliers. Again, its purity needs to be 99.98%. If we look at the amount of lithium hydroxide that's being produced, Australia is the leader in this area. And it looks as though that this material will be particularly lithium hydroxide rather than lithium carbonate, which will be required for batteries. Okay, so we've got our precursor materials. We want to form them into a single compound, and the process which we would use would be co-precipitation. To do that, we mix our precursors, we precipitate the materials with hydroxide materials so that we get a hydroxide precursor, which we then dry and recover the solids. The lithium's added as a dry material, which is mixed in and then furnaced and calcined and coated to produce the final material. So that process is being undertaken through collaboration with Australian companies and the Future Battery Industry, CRC, here in Australia and in Perth. A second material which I've mentioned is the anode, and this is, I just want to go through and look at the process for producing graphite in Australia and what we need to do. Graphite is important because it's actually the main component in lithium battery. More than 50% of a lithium battery is graphite. If we've looked briefly at the value chain, but if we go back and look at the stages of processing for this material, we find that we start with natural graphite. Oh, excuse me, let's go back one slide. We start with natural graphite and we take it through a spheronizing process and purifying. We then need to coat that material and we can hybridize it with synthetic graphite. It's important then that we actually integrate this material with nanosilicon addition. And the way that we do this increases the performance of the anode significantly. The team that we've brought together in a collaboration is a research team of the University of Melbourne, Department of Chemical Engineering, CSIRO's Manufacturing Division, and QUT's lithium-ion battery pilot plant has teamed up with an Australian resource group. Cyril Resources, the world's largest graphite resource and mine, Talbot, Europe's largest and purest graphite resource, an Australian company, and Ecograph, which is going to graphitize and purify the process and have that plant here in Australia. We've also got technical support from companies such as Calix, which produces a novel large-scale thermal processing of the graphite. And as I mentioned, the nanosilicon addition is through industry support from Antio Diagnostics. Spheronizing is from NARA. So together, by putting together our research team, our resource team, and our technical team, we've got all stages of this process that we need to produce a commercially viable international levels of anode material here in Australia. To join these materials up in a battery and have it work, we need an electrolyte, as I mentioned. So we're looking here to have a future electrolyte systems project as well to produce safe, high temperature electrolyte. Again, we have a collaboration between our research group. Deakin University is leading that group. University of Technology Sydney, QUT, CSIRO are teaming up with Solvionics, Boron Molecular, Calix and Talbot to produce these materials again here in Australia. Now, one of the things that's important about the electrolyte material is it's linked to the other parts of the battery process chain. So when we produce a cathode material, it has to be validated in a full cell. Same with anode materials. And so what we do is we put them together with the electrolytes in a cell. Now they react with the electrolyte in the first charge and discharge cycle. So it's very important that we develop appropriate electrolytes here in Australia so that we can validate our materials. The Future Electrolytes project will look at things such as electrolyte formulations, the separator materials which are most appropriate, and binders for producing the materials in our inks that bring all these materials together. In addition, we need to consider enhancing cell performance, so we want to look at electrolyte systems development, the formation of solid electrolyte interfaces when we first charge these batteries, and then to electrolytes which will help in cell formation and optimization. Now, once we've put these three lots of materials, our cathode, our anode, and our electrolyte together, we need to then put them together in a standard cell format, something that's internationally accepted as a standard, and test those materials. This will help validate our materials as a commercial product. Now, one of the projects that we've done to support this is an electrochemical and testing cell fabrication project. Now, there is an existing baseline facility here in Australia for electrochemical testing. So it tests the performance of cathodes, anodes, and electrolytes in standard cell formats. It also, as I mentioned, tests advanced separator materials and puts these together and forms a database for our research groups. And so we're going to build on this existing infrastructure which already exists here in Australia. The sorts of things we look at from our materials suppliers are the powder characteristics, composition, purity, agglomerate size, density, porosity, those sorts of physical characteristics. We then put them together in electrochemical cells. We look at ink formulations, coating, density, and cell construction. And finally, when we test these materials in full cells, we look at cycle life, cyclability, conductivity, and safety. So this is an essential part of giving feedback on our materials. So parts of this particular project will look at standard fabrication cells using commercial materials, and we'll benchmark these materials. What we will then do is produce cells using our Australian-based materials and compare them against those benchmarks. And then we'll go and look at validating those materials so that they're suitable for sale around the world. So we'll look at certification, safety standards, etc. So this gives us a support for materials development here in Australia. The next part of the process, which we're looking at in the supply chain, is to test the materials in modules and batteries. And in particular, when these materials go out to the consumer, they want to know about performance and safety in particular. So as part of the Future Battery Industry CRC, we're establishing the National Battery Testing Centre on a 60-hectare site in Brisbane. So this will integrate with a clean energy centre, which will integrate with a hydrogen project, the solar projects, and microgrid arrays, so that we can do real scale testing of these materials. We'll look at modules, the assembly, we'll look at abuse conditions and safety, balancing systems, battery management systems, and we'll also look at pack development and cycling. So we're going to be able to test Australian-based products against international products, validate them, and provide feedback on their safety. The sort of things that we have to do is test cells, and that's around up to 0 to 10 volts. We put those together into modules, which we then put together in packs for applications, and that can be anything up to 1,000 volts for testing. So we have to have fairly sophisticated equipment, and this is being established at the National Battery Testing Centre. It's not only going to be lithium batteries which we'll be testing, but a new group of materials based on vanadium and battery systems based on vanadium called redox flow. We have a number of companies in Australia that are now mining vanadium, and they're looking towards introducing these vanadium batteries as well. So we need to make sure that we've got support systems as well for that group of companies. And so the National Battery Testing Centre will also test these materials. Again, the range of equipment will be internationally based standards, but we'll be able to test from 0 up to 1,000 volts and up to 1,000 amps in a particular system. So if we look at what type of system we're putting together for testing, we're going to have solar arrays where we involve different types of photovoltaics. We're going to also have the grid will then supply into electrolyzers to produce hydrogen of different through different means. We'll have battery systems that will connect in plug and play style of format, which will test lithium, vanadium systems, and other battery systems. And then we will produce from the electrolyzers the hydrogen. The battery systems will support 24-hour production of those materials, and it'll help our battery systems to be evaluated in terms of microgrid, so DC-DC grid, as well as AC-DC grid testing. So if we look at the overall process, we've taken our mined minerals, we've processed those materials, we're supporting the development of active battery materials such as active cathode materials, anodes, electrolytes, and we've built a support system around electrochemical testing and cell fabrication, and now all the way out to complete testing centres for battery applications in Australia. Hopefully we can then participate in the full supply chain that's available to Australia from its enormous resources in battery materials. It's all based on the fact that our mining capability makes us #1 in the world in terms of those resources. I'm hoping that through this process, we can actually be one of the leaders in the world in terms of our battery supply chain. I have to acknowledge a significant collaboration between our universities, our corporate companies across the board, and the infrastructure that's being supported through the Future Battery Industry CRC. Thank you for your time, and I look forward to talking to you soon.
Hello, everyone, and thank you for joining us for this live Q&A discussion this morning. I'm going to hand over to Alan Taylor, who's going to moderate the discussion. Over to you, Alan.
Well, good morning, everyone, or hello, wherever you are. Just a few words here to explain that Professor Talbot was unable to make the Q&A this morning, so apologizes. And we've got a very able substitution in Jose Alauco, who's very kindly agreed to join us, and he'll also join the panel tonight instead of Peter. Jose is a professional fellow at the Institute of Future Environments at Queensland University of Technology. He's been involved in R&D from the lab up to pilot plant scale on superconductors, battery, water treatment, and other nanotechnology materials for almost 3 decades, both in academic and commercial organizations. He has worked collaboratively with major players in the battery industry for more than a decade. So he's more than qualified to be, let's say, pinch hitting for Peter this morning. So I've already got we've got a couple already of questions. Firstly, it's from Desi Amalia. And she says that, I think, I'm not sure if Desi's a male or female, but anyway, since Australia does not have natural graphite, is it possible to synthesize the graphite from coal, which Australia does have?
I think not all the coals have the right characteristics, so there needs to be some purification. And I think the cost of purifying and selecting it might become an issue. But that question is more like for the mineral processing experts. But the quality of the source graphite is important to determine whether it will result in a good product or not. That's my that's the information that I have at this stage.
Okay, that's fine. And next from Mike Dry. The Tesla people were talking about anodes using metallurgical silicon and a flexible binder instead of graphite. Do you have any thoughts on that?
Yeah, I was observing some of the Tesla's release of information. It's a bit difficult to make a clear statement without all the information, but there are many requirements for a material to operate. One needs electronic conduction, one needs lithium diffusion. The binder itself would not be an active material. So how much binder will be required to absorb the mechanical deformation of the silicon is an open question. It's not clearly described in the Tesla's reports yet. And if this flexible material will also not interfere with solid electrolyte interface formation and all those other aspects, it's still a bit of an open question. So I think that release could be a little bit like a vision more than a readily available reality. But I'm not sure. I'm just sort of keeping an eye for more technical details on that.
Thank you. Just keep questions coming in. If I don't have one at the moment, so there's opportunity if you need a question. I'll just put one in myself just to keep the ball rolling along. And I'll ask one, just how far up the battery supply chain do you think that Australia can go? The precursors or up the batteries? How far do you think we're heading?
I think Australia could go all the way to final application, but it has to be a staged development. So the immediate generation of economic activity will naturally come from the mining and then perhaps the precursor material. But moving up the value chain, it gives an extraordinary opportunity for Australia to keep climbing that ladder. If renewables and vehicle electrification multiply because the cost of batteries is possible to drop them down because of a scale of production and all that, it's possible that every country needs a large volume of batteries that would justify local production. So I think it is a matter of the economics and the desire to take up the opportunity. So I think my view is that if renewables take up, and recent election of Joe Biden, he said he will really emphasize renewables and all that, it's possible that the multiplication of use of batteries will be phenomenal. So it just depends on the cost.
Okay. If anyone has more questions, we've got a few more minutes. In the meantime, I won't allow any gap in the opportunity for a discussion. So I'll throw another one in myself. And I just ask, with all this work we're going on and the future environments and so on, and all the work that we're doing in around Australia, what contribution do you think there's reasonable to believe that Australia can or will make to, let's say, battery technology development in general?
Yeah, I think Australia demonstrates a lot of expertise when manufacturing and production becomes extremely large scale. And there are examples in the mining industry, in agriculture. Hopefully, that type of expertise can also become in a massive scale production of batteries and all the stages. So I think Australia has time and again demonstrated a very good ability to develop very efficient processes. And I think that could have a massive impact in the cost of production of battery materials. So I think Australia could be a great contributor in developing those very efficient processes. Yeah. And I hope it becomes a reality.
We certainly have the materials And we seem to have in the area of research, I think you mentioned earlier that around the world there is a strong involvement of government in terms of funding. And I think that's a potential game changer for any country. Do you think that here in Australia we have that will? I know you're not a politician, but is your impression that we have that will to actually to do something real this time? Because Australia has always been an exporter of things and has not been a good downstream processor.
Well, I've been in applied research for several decades now, and the recent efforts of the Future Battery Industry 3RC, to me, is unprecedented. The level of cooperation that is attempted to be established around Australia is unprecedented. Mm. And the collaboration between industry and academics at that level, I also think is unprecedented. So personally, I find this as a lifetime opportunity. And the economic opportunity to get involved in batteries, I think, is also like a once in a lifetime opportunity. So I think there is a strong will to develop it. And it's just a matter of staging the activities, in my view, so that the economic returns become more immediate, so then that can be reinvested and we can move up the value add chain.
Okay, another question I've got about the University of Queensland, where you are. It was, I think, pretty exciting for people when we all found out that they had actually made a battery and were doing a lot of work on batteries and some pioneering work. And just from the point of view of your university there, what do you think the contribution of that pioneering battery work that's been done, the contribution to the development of batteries as a whole in Australia?
I think the experience to actually get involved in making the commercial style cells, it gives you a better understanding of the costs involved. Even though we don't get a full understanding because it's just a pilot, commercial scale will demand more specialized equipment. But the equipment we use is for demonstrating the concepts. But battery materials, some of them could be developed with very exciting properties, but if the cost is too high or is too complex to produce, they may not reach the market. So that understanding and that work with industry that understands cost of production and feasibility for scale up, it takes time to develop the expertise. And I think sometimes academics do not get involved given circumstances to practice that type of thinking. So I think that's the type of interaction that can make a link between the basics, fundamental science, and the applied product. So I think it's, that could be the contribution of this type of piloting efforts.
Good. Well, Alison, I think we've reached about our time here. I've got another question, but I don't think I've got time to ask it. But we will have, of course, time to ask the panel tonight. So I hope all the delegates will join the panel. We've got a very, very excellent panel. I think it's quite an amazing panel we've got, and I think it could be really a landmark panel that we could get some terrific discussions. But a lot of that will depend on people asking the right questions. So please join tonight, and Jose will be part of that. We're looking forward to it. So I'll hand back to you, Alison, and thank you, Jose.
Thank you.
Thanks very much. We will make this recording available to everyone at the end of the presentation, and Jose has kindly offered his email address for anyone who needs to contact us. So thank you to you both.
Thank you.